All right, thanks for the introduction and good afternoon to everyone. So today I really want to just give you a very brief overview of a project I've been working on for the past sort of year and a half on and off, an interesting one in New York City. This particular project is a rail project. It's located on the Upper West Side of New York City. It's a 26-acre site, so a very large site. It's actually split into east and west by 11th Avenue, which you see running through the centre there, and so we refer to each of the yards as the East Yard and the West Yard. And the focus of this scope really was the East Yard. On the site you can actually see around the outsides there's a number of ancillary buildings used for maintenance, and really the purpose of this yard is actually to store cars during off-peak hours. So rush hour, they come into Penn Station, drop off passengers, and they're stored here in the middle of the day before they go back out in rush hour in the afternoon. They perform various maintenance, cleaning and so forth during the day. So what's the difference? I guess why am I working on this project? In an open rail yard, you have a fire in there. What basically happens is that smoke then vents to the atmosphere, and we don't really have a large risk. Occupants can get out relatively easily. So I was actually, or ARUP was rather, brought onto the project by a developer who's looking then to build an overbuild on that site. What they're actually intending to do there is to develop 12 different high-rise buildings on that site, 10 acres of public space, parks and various different cultural facilities, and a public school and so forth, to really create what is essentially a wasted space now into something that can be used by the public and various commercial people. And as you can see here, when you build something over the top, we're going to have smoke down in that layer, creating a risk for the maintenance staff that are working within that space. So stepping through our design methodology, as I said earlier, the project scope really is the East Yard for this portion of the work that I'm talking about today, with a view to the West Yard strategy as well. ARUP actually provided MEP for the lower portion, as well as lighting and life safety. Interestingly, we also did CFD for the HVAC as well. We did that within Fluent. The work today is within FDS. So the key objectives really were clearly life safety to begin with, also looking at firefighter intervention and making sure our conditions within the space were suitable for them, meeting NFPA 130 and applicable local codes, New York State and Long Island Railroad requirements. And also from the client side, optimizing the system so that we could get a system in there that was cost effective and buildable. The overarching theme for us really was to keep it simple, keep those systems simple. And from a technical point, one of our objectives was to keep it independent from the Amtrak yards and Penn Station to the east of the site, so that we weren't dependent on their systems and vice versa. So stepping through the rest of the methodology, it's really typical of the SFPE guide, which many of you will be familiar with, and I'll give you a brief overview of each of those points. So as I mentioned, the key life safety criteria are really looking at the evacuation portion early on when the fire actually starts off and we get some sort of alarm, getting those maintenance staff out quickly, and then making the conditions suitable for the firefighters as well. The criteria for those is somewhat different, as you'll be generally familiar with. For occupants, we're looking at your standard visibility and temperature, but then for firefighters, they've got their full turnout gear, which means that they've usually got breathing apparatus, so visibility and toxicity are less of an issue, except visibility in terms of being able to find the fire and walk through clearly. And in terms of thermal exposure, they can withstand a much higher temperature than occupants. So the critical metric really was to look at getting people out early. And what we really needed to do was have a clear understanding of what the available exits were and what the occupant load was within that space. So working with the Long Island Railroad, we were able to establish what the occupant load was for the space, which was roughly 125 occupants within each of the various maintenance buildings, and then up to 25 within the yard. So it's quite a low occupant load when you consider the types of buildings that we're often working with. There were 6 exits scattered around the site, but really the critical thing for this site was travel distance. Because you've got various train consists on the site, some of the occupants would have to walk up to 890 feet to get to an exit because you can't actually transfer between the trains. So for this project, we did actually run a model, but it's important to note that particularly with a low occupant load like this, we didn't really need to. That we could actually establish what our performance criteria is just with doing our basic NFPA 130 hand calculations. But the real benefit of running a model in this type of situation is improving the project deliverable, which is all about impressing our client and also being able to convey the design to the authorities as well, which really helps to really convey what we're trying to achieve within the space and give them a sense of the conditions. So stepping through this in terms of our performance criteria, you'll be largely familiar with this. We break it down into detection, notification, pre-movement and movement time to establish our evacuation time, and then having some minimum margin of safety, which we typically aspire to be 100% of the movement time. And we get an overall time that is really our starting point in terms of what we need to maintain with our smoke systems. So a summary of that, we had basically a range of 8 to 11 minutes for our evacuation time using sprinkler activation, typical notification and pre-movement times, and then using the modelling to establish the movement time. If we incorporate the margin of safety, we were looking at the range of 13 to 17 minutes that we need to maintain occupant tenability. So getting into the design fire, the actual design fire curves you'll see here are governed by Long Island Railroad, which actually works quite closely with Amtrak, and they have two fire curves. They have a single rail car, which grows up to 5 megawatts, then to 10, and then eventually up to 31 megawatts at the peak heat release rate. And they also have a 2 rail car fire, which basically involves roughly the 23rd minute fire spreading from one car to the other. And those really were kind of the basis for our design fires. If we look at that in the context of what we're trying to achieve, which is really occupant evacuation and secondly firefighter intervention, you can see the evacuation actually occurs before the two fire curves actually separate. So it's really within that early period up to 10 megawatts, and then firefighter operations then on. The second thing to note really there is that firefighters will be on the site quite early. They're actually required to be on a site after an alarm within 4 minutes. So they'll be getting water onto that fire quite easily before the 23-minute portion, before it spreads to the second car. Okay, so looking more at the 2-car rail car fire, what we wanted to look at was have an understanding of that. And really what that is it's governed by essentially fire spreading from one to the other. But what we actually wanted to question there is what is the effect of sprinklers? This case here is actually based on an unsprinklered case. We wanted to understand what the benefit was of providing sprinklers in that space and if that could actually prevent fire spread. So what we did to start off with in the design, we actually set up two models. We set up a side-by-side arrangement which reflected the Amtrak setup. And we also set up an end-to-end arrangement which simulates 2 cars in a 8-car consist, for example. This is a sprinklered case. We've got tracer particles for smoke in black, and the blue represents the sprinklers. Okay, so looking at the results in more detail, the 3 lines that you can see there represent the various criteria for polycarbonate glazing, which is the glazing used in these trains. The bottom is for the initial constraint for deformation. So once you get to 138C, deformation begins to occur. Once you get to 310, you start getting melting, and then at 550 degrees C, you're actually getting ignition. So essentially our criteria in terms of looking at whether sprinklers would actually prevent this, in the range of 138 through to 310, if that temperature was maintained for a significant amount of time, we would consider that to be a failure. So having a look at the results here for our non-sprinklered case as our baseline, these lines actually represent thermocouples on the adjacent car's windows. And as you can see, the temperatures go past the deformation temperature at roughly 20 minutes, and they exceed very, very rapidly up into the next phase. Just for reference, you can see the heat release rate curve and the alignment there. So having a look at the sprinklered case, the first sprinkler discharges at roughly 4 minutes, and that incorporates a 1 minute delay for it being a dry pipe system. It's a dry pipe system because this is an unconditioned space, so we incorporate that delay. Now the maximum temperature, it's quite difficult to see on this graph, but it's well below the 138 degrees C line at the bottom, and it gets roughly up to about 80 degrees C, well below 138. You get some rising towards the end as the heat release rate increases, but it's clearly below that line. Now, the end-to-end sprinkler case also passed. In that situation, it's actually a 2-foot separation as opposed to a 4-foot for the side-by-side. So the results are a little bit closer. Those details are in the paper. You can see those, but these two results really got us to the point where we could confidently say, if we've got sprinklers in place and keeping in mind the fire department will be there when they get there, we could justify using a 31 megawatt fire as opposed to the 52. Okay, so getting to design fire locations. The basis of our study, we looked at 3 basic locations. The first is a design fire near the maintenance building on the southeast side. The second is in the narrow eastern throat region to the right or the east of the site. And that's actually a lower ceiling height region. And the third was on the northwest side, which is beneath one of the towers on the site, where the structure is a little bit lower and a little bit more difficult in terms of maintaining tenability. So one of the things we really wanted to do with this client, we're working with a developer which is largely non-technical, and we really wanted to convey to them the notion that of multiple exhaust points versus single exhaust points, and some of the trade-offs with those. When you're using less exhaust points, you tend to be less efficient, issues such as plug holing and so forth, and you end up with an increased required capacity. Whereas if you're using more inlets, you tend to end up with a more optimized design, but there are issues with constructability and those kind of things. So when we actually came under the project, there was a scheme in place, the 2008 scheme, which is quite small here, but you can see there are 3 exhaust inlet points on the site, and then they're looking to provide make-up air from the east and west portals. And working along the theme of the graph here of more versus less, we wanted to suggest a number of alternatives to really address the capacity, because this design was somewhat problematic because of the proposed capacity in place, and also the reliance on make-up air from the east side of the site, which, as I mentioned earlier, was something we were trying to avoid. So our first scheme was really on the other end of the spectrum. What we actually did was we had 10 discrete exhaust points on the south of the site and 10 supply points on the north of the site. And that served a number of purposes. Really, it made use of the deep structural troughs on the site, which ran north-south and were up to 6 to 7 feet deep. It was independent of the Amtrak yard and the west yard, and it also significantly reduced the exhaust capacity for the site. Some of the issues, though, was because we were actually providing supply air mechanically, there were large demands there, and it was also somewhat difficult in terms of constructability, actually getting each of these exhaust points onto the site. The real point of it, though, is to develop a working solution. We were under a very demanding schedule. What we really wanted to do was get one on the board and prove that we could get something working and then work back to something that was more buildable. So this is the first solution, the first one that I've just discussed. Here we go, ventilation 2. So we went back and we worked with the 2008 concept plan. And really the reason why we did that was because at the point when we got involved with the design, a number of the buildings on the site were already in place, the landscaping was starting to be developed. So the two main points you see there are actually within the site and largely fixed. So we wanted to work with those and see whether we could actually make it work within the design intent. So we largely modified the ventilation scheme somewhat, but we were still providing makeup air on the south and on the north, but just with the two single extract points. As you can see here, these are slice files at 8.2 feet or 2.5 meters above head height. The left is visibility and the right is temperature. And you can see the visibility is somewhat impaired on the north and south, and then temperature is starting to get up to excessive levels on the right. Looking at 30 minutes, which is into the firefighter portion of the timeline, you can see it's really deteriorated within the space. In both levels, temperatures are starting to get excessive as well. I'll get into some of the reasons why that happened, but clearly one of the main things was when you're exhausting, the amount of exhaust that we're doing from two single points, plug holing is a key issue. Efficiency and also robustness, because you're only exhausting from two spots as opposed to good coverage across the site. What we did from there was basically create two plenums. So we have an east plenum and a west plenum with four discrete points within them, discrete slots, and still the same arrangement in terms of supply. With this result, it was worse. So we were a little bit puzzled because it was somewhat counterintuitive in terms of what we expected. And so when we investigated, we started looking at velocity profiles and so forth. What we could see is we essentially underestimated the depth of the plenums and the effect that would have. And what was happening is we would tend to be drawing ambient air still and some of the less hot air as opposed to the upper hot layer. And the other effect of having the plenums is it actually removes some of your smoke reservoir. So what we did is instead of drawing from underneath the plenums, we actually drew from the side of the plenums, and we looked to rectify it using that. This is the schematic. So in doing so, we actually increase the number of exhaust inlets as well. One of the other things we noticed in the early designs is we were getting some mixing, which I'll get into a little bit later, and so we reduced that by 50% as well. This is a velocity profile of that revised scheme. As you can see now, we're pulling in much more of the hot layer up at high level as opposed to the ambient air and the lower temperature air that we were in the previous one. If we look at the results of that, they're markedly improved. We're still getting some visibility impairment on the north and south, but generally the results are starting to go in the right direction. Something to note here, if you look at the scales, you'll see they say good and bad. And one of the key things when you're trying to get across to clients is to really make this as simple as possible so people can understand it, because we're speaking to a technical group here, but I thought I'd leave that in for you. Red being bad, blue being good. Okay, thanks. All right, so this is talking about some of the mixing that we experienced with those north-south plenums, which resulted in some of those visibility issues. And the big thing there was we found that it was causing somewhat of a shearing force and causing that mixing to occur. Which brings us to our current scheme. We had some modifications along the way in terms of capacity and so forth, but essentially what we did was remove the north and south supply and made some modification to the capacities, and that's what we arrived at. This is visibility for the south fire location. As you can see, visibility is quite good across the board. For the east fire location, we're getting some mixing in the throat where the ceiling's a little bit lower. It's also narrow and it's quite close to the throat supply, and a small portion at the south of the site. If we then look at visibility at 60 minutes when the firefighters might be there, as you can see, you're getting some mixing at that end of the site, which is less than desirable, but considering the firefighters will have breathing apparatus and protective gear, it's somewhat acceptable, not to mention that it's within an area away from the actual fire site. If we look at temperature then, which is the key criteria for the fire department, we can see that's well below firefighter criteria of 100 degrees C, and also even for occupants of 60 C. So just travelling through a story of those those designs, we really started with a 2008 scheme that had a small number of inlets and a very high capacity. We worked through the other end of the scale to something that really lowered that capacity but was difficult to construct. Working across the page, we went back to our 2008 scheme, and then we ended up somewhere in the middle where we had a good balance of exhaust inlets and supplies that we could actually build that had a low capacity and met our performance criteria. That's all I have. I'd like to a special thank you for Kurt Schiebel. He's one of my colleagues who helped with much of the work for this.
Do you have any questions for John?
I just want to know how many cells did you have in that grid, and how long were those run times for that model?
That's a great question. Sorry. Great question. As I said, it's a 26-acre site, so the area we were dealing with was probably on the order of 10 acres on the east yard. I believe we were on the order of 7 million for that site, and as you see, the runs actually run out to 60 minutes, which was a requirement of the Long Island Railroad. So the run times of some of those transient runs was 18 days. And we have a number of big clusters. They're pretty competitive clusters, I'd like to think, but it was very demanding. And so what we actually did was, for a lot of the early ones where we had to move quickly on schedule and come up with the designers, we'd model a portion of the fire. So we might model the 10 megawatt portion at a steady state, get something working, then look at the 31 megawatt section, and then once we thought we got to something that was a good design, we'd run the whole thing out. But you know, you can't function on 18-day runs in consulting. It just doesn't work.
Any other questions?
The question from Tanya Sofan online is, was tenability only looked at for temperature and visibility, or were fractional effective dose calculations computed as well for the toxic products of combustion?
No, so we use the typical tenability criteria of temperature and visibility, and the conservative assumption there is that if you're meeting visibility, you're typically meeting the toxicity levels for that space.
All right, thank you very much, John.